Okay, our next topic is tension in the active zone. And this is something you encounter quite commonly in slope stability analysis. And the active zone is, we're basically talking about the top of the slope. And since it's shallow, if you have cohesion in your material properties, you could get the side force or even the bottom force of the slides could end up being negative or in tension, which would basically in effect help hold the slope back. And but soils, even though mathematically we get tension in our Mohr-Coulomb failure envelope, and how we go about defining undrained strength, soils cannot withstand tension, and so this is considered to be unconservative. It'll give you a factor of safety that's too high. And when you're running Utexas ED, here's a case with a cohesion of 400 pounds per square foot, and when you have tension, you'll see this. The green bars represent the normal force at the bottom of each slice, and green means positive, and up here at the top there are negative normal forces at the bottom of the slice. Again, that in effect holds the slope back. There's also this line here. This is called the line of thrust. We'll talk about that a little bit later in the slide, but it represents the location of the resultant force, which is generally in the bottom third or so of the slice, but it can, when you see it go up and down like this, it means there's the transition point resulting from tension. All right, so if you recall from soil mechanics, there's something called Rankine active earth pressures, and if you have a soil with cohesion, and if you plot the horizontal stress, sometimes called lateral stress, versus depth, there's a period at the top where that is negative, and then there's a transition point at a depth ZT, and then it becomes positive. And so you get this negative force up here in this triangle, and then a positive force down here. The value of the horizontal slope, excuse me, this value here is the horizontal stress versus depth, and it's represented by this equation, gamma z tan squared 45 minus v over 2 minus 2c tan 45 minus v over 2. If you set this equation equal to 0 and solve for z, as shown over here, you can solve for the location of this depth where that goes to 0, and that is 2c over gamma tan 45 minus v over 2. And so one of the ways we deal with tension is to assume that a crack occurs in the soil down to a depth of ZT. Now this is not 100% analogous to the forces on the side of a slice in slope stability analysis, because the side forces in this diagram are purely horizontal. They're not always horizontal in slope stability, and furthermore, the strength may not be fully mobilized, and so remember we talked about phi mobilized and C mobilized, and so another reason now, taking another look at what's going on here, if you have a traditional Mohr-Coulomb failure envelope, the cohesion is this intercept here. And once you're on the left side here, let's say you have a circle like this at failure, the major principal stress would be positive. That would be the vertical stress. And the minor principal stress, the horizontal stress, would be over here in the negative zone. So this is, this again, although this makes sense for the purpose of defining a failure envelope equation, it does not mean that the soil truly can withstand tension. Tension, again, tension appears in limit equilibrium computations using slices in 3 different ways. The inner slice forces become negative, or the resultant inner slice force is negative. The normal forces on the base of the slice become negative, and also the line of thrust moves outside of the slice. We talked about that a little bit. So what is the line of thrust? The line of thrust is the location of the resultant inner slice normal force, and is calculated as follows. Z equals the sum of Zi times Fi over the sum of Fi. So this Z is the elevation. So what we're looking at is where, if you take this force distribution shown by these 2 triangles, and up near the top there's going to be a region where it's in tension at the top and compression at the bottom. And if you calculate the resultant, the location of the total resultant side force here, the way you do that is you take the elevation of the resultant force corresponding to this top triangle. We'll call this Fi, and that resultant force will be about 1/3 of the way down here. And then you take the resultant force from this triangle stress distribution, which will be about 1/3 up from the bottom of this triangle, and you multiply that elevation times the force, and then add that up, and then you divide by the sum of the forces. Well, what happens though is once, if the depth gets, based on the depth of the slice, you'll reach a point somewhere along here where the upper force almost balances the lower force. So this sum at the bottom approaches 0. And when that approaches 0, from the upper side, the resultant location becomes infinitely large. And then as you go across some threshold, it's infinitely negative, and then it'll come back. So you get this weird shift in the resultant line of thrust, as we call it. And again, that line of thrust is reported by Eutexis and shown on the screen after you get a solution, and you'll see that weird shape to it. Now, if you don't have any tension anywhere, that line of thrust would be right near the bottom third all the way down, and it works out great. All right, so how do we go about eliminating tension? There are a couple of very simple ways to do it. One is use a modified nonlinear Mohr-Coulomb failure envelope that does not allow shear strength when the normal stress becomes negative, or we can add a tension crack. So as we've discussed in our lecture on Eutexis, there is an option in the material properties to enter the geometry of a non-linear Mohr-Coulomb strength envelope. And so, for example, instead of just giving a C and phi, you can give a set of C and phi coordinates. So this would be 0, 0, 0, 0, 0, C, and then, excuse me, it would be tau sigma coordinates, not C phi coordinates. It would be the 2 coordinates here would be the normal stress and the shear stress. So 0, 0, 0, 0, 0 tau, 0 C, and then, some value up here. Another way to do that is you can, instead of making it vertical here, the farthest over you're going to allow this circle to get is right here. You don't want that circle to go to the left, so you could create a series of points along here and then have it linear from that point on. And that way, it will never, this does not allow the shear strength to ever go negative, and so this is a very simple way to handle that. Another thing we can do is add a tension crack. If you add a tension crack, you just give it the depth of a crack. You've seen that in the input to UTexas ED. It's just a depth from the top of the slope. And that depth will be equal to, based on the equation we saw earlier, and now we're plugging in developed cohesion and friction, 2c over gamma times tangent 45 minus v over 2. But this will be the developed cohesion and the developed friction. Now, the issue is, so you could say, well, I'll just use this to calculate the depth of my crack and then run the analysis. Well, you need to know the friction angle. So you can guess at the friction angle and then run your analysis and then see if you have any tension left. You don't want to make that too deep or you're going to be overly conservative. Another approach you can use is you can iteratively vary the depth of the crack, calculate the factor of safety, and then plot the factor of safety versus the depth of the crack. And for this example problem shown here, you get a factor of safety curve like this. So what you'd want to use then is a factor of a depth of about 9 feet. That gives you the minimum or most conservative factor of safety. Okay. So that's a pretty simple approach.